Our goal for this video is to talk about the activity manuals from Chapter 11, Section 4. But before we get started with those activity manuals, we're going to talk about the concept of odds. Now, odds and probability, very similar, but you need to stop and think about how the odds are calculated. For example, if I say the probability of an event happening is 3/4, 3 out of 4. That means there are 4 different ways it can happen, and 3 of them are included in what we're interested in. So the probability of our event happening is 3 out of 4. If I want to talk about odds, though, I don't include the total. I talk about what is in favor of and what is against. So for this particular event, the odds in favor of our event happening are 3 to 1, because out of the total of 4 ways it can go, 3 of them are in our favor, the event that we're looking for. 1 of them is against. If I say the odds against our event happening, I would say 1 to 3. Another example, if I told you that the odds in favor of a particular guinea pig winning the race were 3 to 7. I tell you that the odds in favor of the guinea pig winning are 3 to 7. What's the probability it will win? The probability that our guinea pig is going to win 3 out of a total of 10 different ways the race could go. Well, if this is true, then what are the odds against our guinea pig winning? Well, if the odds in favor are 3 to 7, the odds against are 7 to 3. And the probability that our guinea pig won't win, so the complement of that, the probability that it will lose, would be 7 out of 10. So when I'm talking about odds, I'm taking that denominator, that sample space, all the ways things can go, and I'm splitting it up. And when I address the odds, I have both pieces mentioned separately. Odds in favor are the way our event that we're interested in would happen. Odds against are the numbers of ways it won't happen. One more time, if I said the probability of rain today is 5 out of 10. Well, that reduces to 1/2, right? So that means the odds in favor of it raining are 1 to 1. They're even. Even odds that it will rain, even odds that it won't rain. Odds in favor are 1 to 1. Odds against are 1 to 1. Okay, so now let's talk about a simulation. This particular simulation, go ahead and read this before you go forward in the with the video. Go ahead and read the setup and see what you think. Basically, should you take the bet that if you're standing in a group of 5 people, at least 2 of those 5 people are going to be born in the same month? What do you think? Do you think it's likely or unlikely that at least 2 people in a group of 5 will have their birthday in the same month? Well, there's a couple of different ways you can figure this out. You could calculate experimental probability by doing a simulation, or you could calculate the theoretical probability. We're not going to do the experiment. You are welcome to do the experiment, to do the simulation. If you feel like you need practice with simulations, with experiments, absolutely go for it. We're going to talk about this front page and then about number 4 on the back. So if you're going to do a simulation where you need 12 months represented, you could use 12 slips of paper so that each slip of paper represents a month, right? 12 months, 12 slips of paper. Why would you draw each 5 times for each trial? Well, you would draw 5 times because we're talking about groups of 5. So there are 5 people in each group. Why would you need to put the slip of paper back after it had been drawn? Well, the whole point is to figure out whether or not it's likely, or exactly how likely it might be, for there to be 2 or more people born in the same month. If I draw a month and I don't put it back, then I can't have 2 people drawn in the same month. So each month has to be possible for every draw. So let's think about this. If I were going to perform a simulation and each trial took 5 draws, if I were going to conduct 20 trials, it talks down here about doing 20 trials. If I were going to do 20 trials, how many times would I have to draw a piece of paper? Well, 20 trials, 5 draws each. So I would have to draw 100 times to conduct the simulation using 12 pieces of paper. Another way it suggests you do the simulation is by combining a coin with a die. How could you set up and assign things so that if you pick a coin and a die, you would be able to represent all 12 months? Well, typically, you've got heads and tails for the coin, and then you've got 1 through 6 on the die. So you've got your coin and you've got your die. So you've got heads 1 through 6 and tails 1 through 6. There are 12 possibilities right there. So heads 1 through 6 may account for January through June. And then tails 1 through 6 would be July through December. So that if you flip a coin and get tails, you roll the die and you get a 6. Tails 6 would be December. Heads 6 would be June. Heads 1 would be January. Tails 1 would be July. And then you would assign the months in between accordingly. Let's look at the next page of this. Like I said, we're not actually going to perform the trials. We're not going to do the simulation that it suggests as a group. You are welcome to do it to see what your outcomes might be. If you were going to represent your results to estimate the probability that 2 or more people in a group of 5 will have their birthday in the same month, that percentage, that fraction, would be the number of trials that ended up having a repeated month, number of trials with a repeated month, over 20 if you did 20 trials. So here's my box, my grid. It has 20, it's a 4 by 5. So I've got 20 different trials lined out. I would have 5 results in each of those. Anytime I had a result repeated within a box, it counts as a trial with a repeated month. That's experimental or empirical probability. It's based on the number of trials. Theoretical probability, however, is based on the number of possible outcomes in the sample space. So let's talk about theoretical probability for this problem. This theoretical probability will have their birthday in the same month can be computed using fundamental counting principle. The event E is that 2 or more people out of 5 have the same birth month. So what would be the complement of E? E prime, or if I put the line over E, well, that complement of E would be that all 5 were born in a different month. All 5 were born in a different month. My event would happen if 2 out of the 5 were in the same month, 3 out of the 5, 4 out of the 5, or all 5 out of the 5 were born in the same month. The only thing that is the complement that is not included in the event we're looking for is that all 5 are born in a different month. Well, how many different ways can 5 people in a group be born in different months? I need to come up with the size of my sample space. This is where I use the fundamental counting principle, because there are 12 months in a year and I have 5 different people. So that would be 12 times 12 times itself 5 times. So that's my denominator. That's the total number of outcomes in the sample space. My sample space is 12 to the 5th power. That's the number of different outcomes I could have. Now, the only outcome that is not included in my event is this complement, and it would be the outcome that everyone has a different birth month. Well, if that happens, then I'm not going to be replacing. Let's read this paragraph. There are 12 possibilities for the birth month of the first person. Once that birth month is set, there are only 11 months left for the second person. Because our goal for this complement, E prime or E complement, is that two people don't share the same birth month. Everybody's born in a different month. So this is the case where we don't want replacement. So I talked to the first person. They said they were born in March. March can't be used again. Second person is born in February. February can't be used again. Third person's born in April. April can't be used again. Fourth person's born in May. It can't be used again. And then the last person was born in June. So that's the different numbers of outcomes that happen if everyone is born in a different month. That's the different ways that can happen. So what's the probability of this complement, that nobody shares the same birth month? Well, the probability of this complement is going to be this number of outcomes out of the size of the sample space, this 12 to the 5th power. If I plug that into my calculator, I figure out that the likelihood that everyone is born in a different month comes out to be about 0.38 or 38%. So here is a probability fact that if two events are complementary, the probability of the event is 1 minus the probability of the complement. So if the complement has a probability of 0.38, what's the probability of our event? The fact that 2 or more people are born in the same month? Well, the probability of the event that we're interested in would be 1 minus that probability of the complement, or about 0.62. So it's actually pretty likely that if you're in a group of 5 people, at least 2 of you have been born in the same month. Now this is a fun one to do in class because we go around the room and we can get different groupings of 5 really quickly and ask and find out just how often for our groups we can get 2 or more in the same group that have been born in the same month. All right, let's switch to this last activity manual of the semester and talk about expected value. All right, so let's talk about expected value of a game. Again, we can't play the game very well. Read the rules for the game and see what you think. You'll see that you've got a spinner set up, and we've done activities with geometric probabilities. So you can, you know what to do with a spinner that has different labeled sectors. You see that there are 4 sectors labeled red and yellow. In the 2-player game, players will take turns spinning the spinner. If the pointer lands on the same color on both spins, player 1 gets a point. If the spinner lands on different colors each time, however, the second player gets 2 points. So you're going to spin 2 times each round. Either they both land on yellow or they both land on red and player 1 gets a point, or they land on different colors and player 2 gets 2 points that round. So player 1 gets 1 point if it goes their way. Player 2 gets 2 points if it goes their way every single round. You could go ahead and do this. You know how to use a paperclip? Do you know how to use a paperclip? We didn't do that activity. If you take a paperclip and stretch it out, so I recommend finding a smaller paperclip for this to create a spinner. Sorry guys, my supplies are not everywhere I expect them to be. So if you take a small paper clip and you straighten out the outside rim so that it's like this, then you have a spinner with a pointy end. And then you take your pen and you place your pen right in the center of the spinner, just like that, to hold the paper clip, and you spin, just like that. So you just flip it. You could go ahead and do rounds. Every time you spin twice, you're going to record it. So like this landed on red, count that as my first spin, and then I start again and that lands on red. Same color, so player 1 gets 1 point for that round. And then another round, I'm going to spin twice. That one lands on I'm not sure. Let me spin again. Let's say that one lands on red because I'm going by the straight. And then that one lands on red. Player 1 gets 1 point again. So you're going to do 10 rounds and total up your points. Pause the video, go ahead and do that. Then decide who won the game. Well, it totally depends on your outcome. But now we're going to compute the theoretical probability. That's our experimental or our empirical or empirical probability. It's how you would see who got the most points to see who wins, player 1 or player 2. Then theoretical probability, we compute the probability of the sample space. Well, based on the geometric probability of our spinner, both red and yellow occupy the same amount of space. So we're going to spin twice. Let's do a organized tree diagram. My first spin can land on red or yellow. They're equally likely. Each is weighted a half of the area of the spinner. And then I start over. And because nothing changes for that second set of spins, I've got the same possible outcomes. And we have just created a weighted tree diagram. Red, yellow, red, yellow. What's the probability that I do 2 spins and they land on the same color? Well, this branch is the same color. A half times a half is a fourth. This branch is the same color. A half times a half is a fourth. And 1/4 plus 1/4 is 2/4, which is a half. What's the probability that the 2 spins land on different colors? Well, that would be either red, yellow, or yellow, red. Same set of probabilities. A fourth and a fourth makes a half. So is this a fair game? Well, they have the same sets of probabilities, right? So that makes it fair. No, it is not. But why is it not a fair game? Because the spinner is set up as such that it is a fair game. Well, it's not a fair game because of the point values. The probabilities are the same, but the point values are not. Who does this game favor? Well, the game favors player 2 because if they win, if they get different colors, then they get 2 points. While if player 1 wins, they just get 1 point, and each outcome is equally likely. How could you change it to make it a fair game? Well, you could make everyone gets the same points. Everyone gets maybe 1 point a turn when they win. If it lands on player 1 same color, they get 1 point. If it lands on different colors, player 2 just gets 1 point instead of 2 points. That would make it fair. Okay, so speaking of fair games, a game is fair if the expected outcome, that expected value, is 0. Because if the expected value is 0, you expect to win as much as you spend. Does that make sense? I'm sure you can guess that when you go to Vegas, for example, or go to a carnival, that you can't really expect a fair game. If you could expect a fair game, then they're not making money. Chances are really, really good. Okay, let's look at this first example. A carnival game costs $3 to play. A player spins this spinner 1 time. If it lands on you lose, they've lost their $3. If it lands on you win, they won $4 or $7. But remember, they've already spent 3, correct? So if they land here, what they've actually won is $1. And if they land here, they've won $4. Because you've got to take out the amount you had to pay to play. Suppose you played this game 100 times. How many times would you expect to just flat out lose your $3? Think about geometric probabilities. Well, since half of my spinner is the you lose sector, I would expect that out of 100 times, 50 times it would land on you lose. About 25 of those spins should land on this sector where I win $1, and the other 25 should land on that sector where I win $4. Okay, let's look at that next page. So theoretically, you know what? I'm going to take advantage of this. There we go. So theoretically, if you played 100 games, you would lose $3 in 50 of those games. gain $1 in 25 and gain $4 in 25 games, what would be your total gains or losses? Well, let's look at it. If you lose $3, 50 games, you gain $1 for 25 games, and you gain $4 for 25 games. If I do that computation, I get that I would lose over the course of 100 games, I would expect to lose $25 over 100 games. Well, if I expect to lose $25 over 100 games, then what is that per game? Well, that would be a loss of 25 cents per game, because $25 out of 100 games comes out to 25 cents a game. Now, here's my question. Am I ever actually losing a quarter? Well, no, that's not one of the options. The options were you lose your $3, you make $1, or you make $4 based on where it lands. This is the expected average outcome. Is this a fair game? Well, no, because its expected outcome tells us that on average, you will lose money. Now, does everybody lose money? Well, no, absolutely not. If everybody lost money, they couldn't get anybody to play. Some people will win, but on average, you will lose 25 cents a game. Your theoretical winning or losses per turn on a game like this are called expected value. The expected value is computed by taking the probability of losing times the -3, because that's what you lost for this game. The probability of winning $1 times 1 plus the probability of winning $4 times 4 to get my 25-cent loss. Now, okay. Why do we multiply the probability of losing $3 by a -3? Well, because a negative shows a loss. What does the answer -25 cents mean in terms of the game? Well, it means that on average, you can expect to lose about 25 cents a game. So if you played 4 games, you expect to lose about $1. If you played 4 games, how much would it cost you to play 4 games? Well, it's $3 a spin. So that would be $12 that you would give them. So you're going to get back out on 4 games. You're going to maybe win about twice. So you expect to get about $11 back over the 4 games. And then we have a general, and this is what I was really marking up, I thought. This is our general expected value computation. A game is fair if the expected value is 0. Because that way it doesn't favor you or the house. All right, consider this casino game. A player pays $1 to roll 2 dice. If the player wins $5, if he or she rolls a sum of 7 or 11, and loses the $1 if he or she rolls any other sum. Now it says to do a 25 trials. So you're going to roll your dice 25 times. And you're going to keep a tally. Every time you roll a 7 or 11, you put a mark in the gains. Every time you don't roll a 7 or 11, you put a mark in the losses until you get your tally for your 25 game trial. And see whether or not you think this is a fair game. Now, go ahead and pause the video and do that. But we already talked about 7 or 11. Do you remember us talking about sums when we introduced probability? Those sums of 7 and 11 aren't super common. Sums like 3, 4, 5, 6, well, 4, 5, 6 especially are more common. So we don't have great odds at rolling a 7 or 11. Once you've computed your experimental or empirical probability, it wants you to go come up with the expected value. Now, expected value is going to be based on your theoretical probability. So you're going to need a sum table. You may have created a sums table. I can't remember if I had you do this or not. Sums tables are easy. We're rolling 2 dice, and the numbers on the dice are 1 through 6. So it's like a multiplication chart, except we're finding sums instead of products. So you're just going to create your sums chart for all the sums of the numbers 1 through 6, and mine is fairly sloppy. I apologize for that. But here's a really quick sum chart where 1 and 1 is 2, 1 and 2 is 3, 1 and 3 is 4, 1 and 4 is 5, 1 and 5 is 6, and 7. And then fill in the remainder. I'm sorry, you couldn't see that at all. Fill in the remainder of the chart. I'm going to pause the video and fill in my chart. Okay, so this is what your sum chart should look like. Now, based on our game, you're interested in the sum of 7 or 11 and then everything else. So let's see, what is the probability of rolling a 7 or 11? We can do this separately or we can do it together. Let's go ahead and do the probability of rolling a 7 and then the probability of rolling 11, and then we will add that together. How many sums do we have? Well, a 6 by 6 chart gives us 36 sums. Out of those 36, how many of them are 7s? You see that you've got 7s along that diagonal line. You have 6 out of 36 that are 7s. How about 11s? Well, you only have 2 sums that give you 11, so 2 out of 36. So what is the probability of rolling a 7 or an 11? There's no intersection there, so I can just add those probabilities up. I get 8 out of 36, which if I divide both of those by 4, I get 2/9. The probability of rolling a 7 or 11 is 2/9. Therefore, what would be the probability of rolling something else, not 7 or 11, the complement of that? Well, we talked about the sums 7 and 11. Not 7 or 11 will be the rest of the sums. If 8 of those sums were 7 or 11, how many of them are not? Well, that would be 28 out of 36, which reduces to 7/9, which you probably didn't even need to calculate because you knew that the probability of an event and its complement are going to add to 1. So if 2/9 of the sums are 7 or 11, the other 7/9 are not. Now, let's calculate expected value. We said that for this game, you pay $1 to roll. You win $5 if you get the sum you want. You lose the $1 if you don't. Now, if I've paid $1 and you give me 5, how much have I made? I've just made $4, correct? So if I roll a 7 or 11, if I get the outcome I want, I make $4. So 2/9 of the time I can expect to make $4. And then the outcome for the other 7/9 of the time is that I lose that $1 that I paid to play. I don't get anything. So that represents the expected outcome of my game. That would give me 8/9 minus 7/9, or 1/9, which is about, if I put it into my calculator, about 11 cents as the expected value of the game. So is this a fair game? Well, no, it is not fair because the expected value is not 0. It's not fair, but it's not fair in our favor. Because the expected outcome is positive, I can expect to make, on average, 11 cents a game, which is pretty cool.